2022, all debate on its identity was put to rest when the Event Horizon telescope unveiled their stunning image of Sagittarius A star. Using a network of telescopes spanning the entire globe, the Event Horizon telescope team spent years carefully combining and correlating their data. The result was a blurry, low-resolution image of the true nightmare sitting within our galaxy's heart. A fuzzy ring of superheated plasma swirls around an evacuated core of pure blackness. At the very center lies the black hole itself, its event horizon preventing any background light from traveling through it. But the immense mass of the supermassive black hole distorts gravity to such a degree that light behind the black hole can instead curve up and around the event horizon, giving us a view behind the monster. The black hole itself appears larger than it really is, again due to the extreme warping of space-time. Lines of sight that would normally graze past the edge of the event horizon instead wrap around it. From our perspective, the globe of the black hole unfolds itself, revealing every angle of it in a single image, producing what's known as the shadow.
Return to the engagement immediately.
That extreme gravity, capable of bending and distorting light like a funhouse mirror, reaches out to the surroundings of the black hole.
Time to step up.
Stars that whip too close to the event horizon risk their doom. As they pass within a critical distance, the gravitational forces tear the star apart in a process called a tidal disruption event.
Damn.
Most of the gas, however, settles into a distant orbit around the black hole. But 25,000 light-years worth of gas and dust sit between us and the center of our galaxy. That gas and dust scatters and absorbs most wavelengths of light, preventing us from seeing the Sagittarius A complex directly. Indeed, if we could, it would be one of the brightest objects in the sky. Radio waves, however, pass through the interstellar medium relatively unaffected, which is why we only saw the first hints of trouble when we turned our radio observatories towards that constellation. But despite the fearsome radiation pouring out of the gas surrounding it, the black hole itself was relatively quiet. It was nothing like the distant quasars with their luminosities millions of times higher. Indeed, except for a faint smudge of radio emission from outside our galaxy, you wouldn't even know that a supermassive black hole was there. But still, the question was asked, could these be related? Could black holes power the quasars? If our galaxy hosted a supermassive black hole, perhaps others did too.
Of course they do.
As cosmologists began to understand the Big Bang Theory more fully, they realized that structures in the universe had to grow slowly. Long ago, there were only small differences in density across the cosmos, with hardly any variations. But over the course of hundreds of millions of years, those density differences
It's so
grew.
unfucking believable to think about hundreds of millions of years.
The only force that really
I
matters
barely
is
live
gravity.
50 or 60.
A patch of matter with a slightly higher density will attract its
And
neighbors,
I'm fucking optimistic.
pulling more matter onto it. That will give it an even stronger gravitational pull, which will in turn pull even more matter towards it, and so on, in a never-ended feedback loop that drives small structures to become big ones, leading eventually to the first stars, clusters, and galaxies. All this gravitational action leads to incredibly high densities in the cores of these structures. It's simply where matter piles up the most. The cores of galaxies host many stars, and those stars are much more massive than average. They live short lives and quickly die, becoming black holes. And packed into such small volumes,
în live, că
black
tot timpul
holes
e altcineva
quickly
până
merge together,
get the
their
plane, oh my
sizes
fucking
growing
god,
out of
5
control,
minutes of looking in the
becoming
menus.
supermassive.
I hate that. Și după aia te dă jos 17 loc on.
The idea that black holes could power quasars was first proposed in 1964, just a year after the identification of the first quasar itself. But most astronomers rejected the idea outright. After all, at the time, black holes were considered a wild and probably unphysical hypothesis. Einstein's general relativity was certainly a radical reshaping of our understanding of gravity, but that didn't mean that every corner of its mathematical structures had to be replicated in the universe. The concept that matter could compress so tightly that no other force could withstand it was outlandish. Surely some process would stop a dead star from catastrophically collapsing into a point of infinite density. But then astronomers came across an intriguing system, known today as Cygnus X1,
mai de mult când eram mic.
a bright source of X-ray radiation in the constellation Cygnus the Swan. Astronomers spent years trying to understand how this star
Da, e still heavy.
so
Dar
many
cred că
X-rays.
upgrade-ul ăla mă înlocuiește pe beltul. Și beltul mi-l trebuie.
Paul Murdin and Charles Thomas Bolton revealed that it was not one
Flaps
star,
on.
but two. The X-rays came not from the invisible companion itself, but from the swirling plasma surrounding it. Detailed observations of that plasma allowed astronomers to
Flaps
calculate
off,
the
gata.
mass, and more importantly, the
Dai speed
density
iară.
of that companion.
N-am știut el
Whatever
până
it
la
was,
chestia asta.
it was more compact than any known star, and more compact than any star possibly could be. Famed astrophysicist Stephen Hawking even bet against the possibility of Cygnus X1
N-am murit niciunul, mă, ești prost.
saying in his book, A Brief History of Time, that when we made the bet in 1975, we were 80% certain that Cygnus X1 was a black
Cine
hole.
trage, mă?
And now, 1988, I would say that we are about 95% certain. The bet is yet to be settled. 10 years later, he
Direct pe tine mă duc.
conceded defeat. Cygnus X1 was the first confirmed black hole. With black holes known to exist, everything clicked into place. The universe readily created stellar mass black holes. These black holes could merge and consume material, swelling them to epic proportions.
Te dus dracu.
These giants would find themselves in the centers of most, if not all, galaxies. And so observations confirmed that everywhere we looked, every galaxy hosted a supermassive black hole. We couldn't see them, they were, and continue to be, too far away to allow us to monitor their orbiting stars directly. With the sophistication of the Event Horizon Telescope, besides our own Sagittarius A star, it has only managed to capture an image of one other galactic core. But astronomers could use the brightness of the quasars themselves as a way to measure the mass of their central black holes. If supermassive black holes did power quasars, then they could use Doppler shifting to estimate
Fac,
the
n-am
black
spart ăla.
hole's mass.
Anterul la bag,
But
pula
for
în
this
el.
to work, the black holes had to somehow
Hărtin.
power the
Ăla hărtin.
quasars. How could they do that if black holes are purely gravitational? How could something that only pulls on the surrounding matter produce
Prietenul meu e aici.
fearsome energies?
Gotta split. Gotta split after that, quick. Că și boții ăștia cu frați. Au un aim uneori de nu înțeleg nimic.
Together with the alerts flashing on the display comes a new, ominous warning chime. A flood of cosmic rays have struck the ship, microscopic
Cine zboară pe aici?
particles slipping through the molecular structures and straight
câte.
into the hearts of the crew. You're determined to go on. Push your ship forward, allowing it to slip into the swirl of plasma in a relativistic frenzy. You don't even
cadavru,
bother
nu?
trying to
Cadavru,
control
da.
it anymore, as the forces here are so
Pică cineva în
strong,
cap, trebuie să-mi dea
so
mie
far
kilo.
beyond known physics that there's no choice but to give in to their mercy. The ship is in uncontrolled freefall.
Iar am intrat în stone, nu vine să cred că intră ăsta în stone.
What you already suspected. The external temperature is reaching millions of degrees, with the internal life support systems beginning to fail. Gripping the armrest, you can do nothing but watch as system after system fails. Frustrated, you swipe away the warnings. There's nothing new they can tell you. After yet another final lurch, one strong enough to throw you against your restraints to the point of bruising, there's a sudden relief.
Tanks!
You bring up the warnings. They're clear. The temperature outside has plummeted to nearly absolute zero. The cosmic rays have vanished, the radiation has subsided. Your ship is still in free fall, but stabilized, no longer tumbling. You activate the external cameras. Shielding retracts, revealing the optics, sending their feed directly to the display. There,
Da, fac, nu lovesc pe ăla, mă. E blindat fraierul. Era să fie ceva.
You launched this mission to the center of the galaxy in the first place. The black hole. cores of galaxies are complicated, busy places.
Da, mă, fraiere, știu că ești acolo să o repari, futu-te în gură să te fut. Să te repară, îl respawn. Mă mir, bă, frate, numai ce n-a dat antiaerul jos, l-am altul în gât. Clever, căcați ăștia, mă.
But within all this brightness and intensity is a dark side. Astronomers estimate that the core of our own galaxy hosts tens of thousands of smaller black holes, a retinue in service to their master at the center. Countless supernova detonations, gravitational tidal interactions, and more tear stars apart, their tattered remains scattered among the close-packed stars. Nothing much lasts long in the intensity of the core.
Maybe don't go that way, huh?
All that chaos sits a thick ring of cold dust, a choking ring of smog within the central city. It is wide, around 1,000 light years thick, and the dust slowly circles around the center. It's also as thick as it is wide, forming a gigantic torus. It is so cold that the molecules and dust within it are neutral. If you were to travel through it, you would hardly notice it due to its low density. Yes! That dusty torus obscures our view of most galactic cores, as it efficiently absorbs most of the radiation coming from within. Only when we look from
Feels
above
very good,
or
feels
below,
very, very
we
good,
get
this
direct view
plane.
of
Oh
the
my god.
mainstream. While calm and non-violent itself, that ring of dust signals an important transition point in the galaxy. Outside the ring, you in the galactic environment, the suburbs, the physics dominated by all the gravitational and electromagnetic forces of the galaxy at large. But within the ring, only one thing matters: the supermassive black hole. It is the central landmark to guide all lost travelers. While even the largest ones take up less than 1% of the total galactic mass, they are by far the most massive singular objects within a galaxy. Far enough away from them, like our own solar system is, away from Sagittarius A star, we don't feel or even notice the black hole. But within the torus of dust, the gravity of the black hole takes over. In this region, the black hole's gravity dictates the motion of every star, every clump of gas, and every speck of dust. It's here that some stars stray dangerously close, their orbital motions bringing their speeds up to a few percent of the speed of light. If they get too close, they're torn to shreds, their atoms joining the trains of gas on their dreadful march towards the event horizon. Even closer to the black hole, that gas begins to lose control. Unable to dictate its own motion, it gets lost in the crowded frenzy, running to incredible speeds, driven by the extreme gravitational environment. It is this process that releases an incredible amount of energy from the simple act of falling. To get an estimate of the amount of energy released, we look at something called the binding energy. To understand binding energy, imagine wanting to move a pile of stones sitting at the bottom of a valley. To move the pile, you must grab each individual stone and bring it to the top of the ridge. Every time you do this, you just overcame the gravitational potential energy of the stone. You can estimate how much energy you need for the entire task by calculating the potential energy of all the stones. Now imagine pulling these stones from the bottom of the valley and sending them so far out into space that they never come back. Now repeat that for every single atom of the Earth, effectively destroying the entire Earth in the process. The amount of energy you would need to obliterate our planet is called the binding energy. For a black hole, imagine dragging a particle from the event horizon all the way out to a distance of a few thousand light years, fighting against the gravity of the black hole the entire time. That is the binding energy of the particle around the black hole, which is equal to the energy released when the particle falls from that distant orbit into the event horizon. And for a typical supermassive black hole, that energy is roughly equal to the rest mass energy of the matter itself. This process is imperfect, and not all the energy available is released as the particle falls. Usually only about 10% of the binding energy converts into other forms. That may not seem like a lot.
Depozita la
Compare that efficiency to the
murit.
0.1% of the rest mass energy released by thermonuclear reactions in the hearts of stars. But this process doesn't lead to an uncontrolled release of energy like a bomb. Instead, the release is slower and in stages. A steady build-up of excitement as material continues to cram towards the black hole. As the gas heats up, it emits radiation. Normally, radiation only makes things warm, but the intensity here is so high that the radiation has a pressure. It is so intense that it can push on things. Imagine the summer sun so strong it literally knocks you over. The radiation pushes the gas, heating it up even more and sending it away from the black hole. But with the gas pushed away, it can't continue heating, and so the radiation dissipates. Eventually, the gas cools down again, allowing it to condense towards the black hole and repeat the accretion process. This cycle of collapse and inflation acts like the piston in a car engine, keeping the flow of gas in check, preventing it from suddenly crashing into the black hole all at once, and keeping quasars shining for millions of years. Yet that is just the beginning. For the gravity around supermassive black holes does not work alone. As any surrounding gas funnels towards the black hole, its orbital speed increases by simple conservation of angular momentum. An ice skater can pull their arms closer to their body to increase their rotation speed, and so can material speed up as it whirls closer to the black hole. But eventually, its inward movement is slowed, the rotation supported by centripetal acceleration, like a planet locked in orbit around a star. And so soon enough, the loose collection of orbiting gas and dust compresses into a tight, thin disk of accretion around the supermassive black hole. All that infalling and compression heats the gas to incredible temperatures. The gravitational potential energy surrounding the black hole converted into heat, friction, and radiation. A simple matter of too much material cramming into too small of a volume. The disk glows, primarily at ultraviolet wavelength, but also across a broad range of the electromagnetic spectrum. In addition, the disk constantly streams out showers of high-energy particles known as cosmic rays, electrons and protons accelerated to nearly the speed of light. Those microscopic bullets can occasionally strike a wandering low-energy photon with infrared or visible wavelengths. And when that happens, the particles transfer their energy to the photons, turning them into high-energy X-rays.
Cred că recoil sau ce dracu are.
The heat of the disk causes the cold atoms and molecules to unbind themselves, forming an electrically charged plasma, the same state of matter as lightning. These rapidly moving electric charges around the black hole create a magnetic field, and very quickly it generates the conditions needed to power a dynamo, a seemingly infinite supply of energy that can turn a small magnetic field into something devastating. Initially, within the disk, the magnetic field lines follow the motion of the gas, swirling in rapid circles around the black hole. But the innermost regions of the disk rotate far faster than the outer regions, forcing the magnetic field lines to pull up on themselves, storing up a tremendous amount of energy. The motion of the gas within the disk isn't smooth and steady. Instead, it's chaotic and turbulent, like a running river, with portions of gas clumping and colliding, waving back and forth as they swirl in a firestorm. When this gas drifts away from the disk, it pulls on the magnetic field like a bit of string. But the difference in rotation from one section of the disk to another twists that loop of the magnetic field around itself. The action of rotation eventually stretches that magnetic field back down into the disk. This is a dynamo at work, which turns chaotic, turbulent motions in the disk into an increasingly strong magnetic field surrounding the black hole. Normally, magnetic fields don't affect the motions of matter, except in very small ways. But as the magnetic forces ratchet up within the accretion disk surrounding the giant black hole, they begin to dominate the motions of material. The closer the gas gets to the black hole, the more unstable the orbits become, and there's a certain special distance known as the innermost stable circular orbit. Any gas that falls below that orbit is doomed. gas falling towards the black hole ends its life at the event horizon, never to be seen again. But some gets caught in the twisting and winding paths of the magnetic field lines. Forces so strong that they channel and guide the gas as it falls. But how does this lead to the radar pinpricks we see in the distant sky? That is still a bit of a mystery. One hypothesis is called the Blanford-Snarek process, named after the two physicists who came up with the idea. The key to this idea is the fact that the black hole itself is rotating. When it does, it drags space-time in the region around it, like moving a heavy coffee table twists the rug beneath. This region, called the ergosphere, forces any object entering into it to rotate along with the black hole. This includes magnetic fields. The strong magnetic fields within the disk punch in and out of the ergosphere, which forces them to twist up on themselves. Twisting fields create a tube of magnetic energy stretching above and below the black hole. Most of the charged particles following those magnetic field lines end up plunging below the event horizon. Some just barely scratch the surface, accelerated by the extreme magnetic energies within the ergosphere. Following the lead of the field lines, the charged particles race away from the black hole in the form of long, thin jets of radiation, lighthouse beams racing out into the dark. This radiation is primarily composed of radio waves, and it is here that we finally find the origins of quasars. The particles in the jets are incredibly powerful, accelerating to nearly the speed of light. They race out of the galactic core and punch through the galaxy together, stretching for up to millions of light years. Eventually, however, they lose steam, the particles interacting with the intergalactic medium that surrounds every galaxy. When they finally stop, they create a high-pressure zone of charged particles. These bubbles transfer heat all the way from the innermost regions surrounding the supermassive black holes into the volumes of entire clusters of galaxies, which can stretch for over 1 million light-years across. That is how powerful these systems are. Not only can they be seen from across the cosmos, but they can raise the average temperature of entire galaxy clusters, the largest gravitationally bound objects in the universe.
The initiative is ours. We've
Măcar aici să câștigăm, nu?
This picture, involving supermassive black holes, the ring of dust surrounding them, the ferocious accretion disk, and the magnetized outflows, explains almost every observation of these galaxies.
Face explosive
As
splash
the
damage.
central core of a galaxy face on, we see the intense radiation from the accretion disk combined with the strong radio emission from the jet, and we recognize it as a quasar. If we happen to be looking directly down the barrel of the jet, then we get the most extreme emission, and we call it a blazar. It's like humanity first encountering cats in astronomical observations. Sometimes they see the whiskers, or a paw, or a swishing tail. Initially, these seem like completely different objects, but over time, we realize that they're really just different perspectives of the same kind of creature. But what of other active galaxies that aren't even loud in the radio spectrum?
Asta cu
The
loconului.
solution here is that not every galactic core is active. To power a quasar, the black hole needs to feed. Without a supply of new material, the entire system shuts down. No gravitational collapse, no accretion disk, no twisting magnetic fields, no relativistic jets, no nothing. This picture also explains why we see no quasars in the nearby universe. Active galactic nuclei can last for incredibly long times. The longest-running quasars can run for over 1 million years. They require constant
Mai reparați atâta voi acolo.
to feed their fires. The early
Fără
universe was
factură.
much smaller than it is today, with galaxies much closer together and undergoing frequent mergers. With every merger, new material finds its way to the center of the galaxy, setting off a feeding event, a new round of quasar activity. But today, with the universe much older and far larger, galaxy mergers do not happen often. With no new supplies of gas, we see no quasars in the local volume of the cosmos. Indeed, our own galactic core is quiet. Although Sagittarius A star hosts stars, dust and gas around it, it's a relatively empty region compared to the cores of quasars. But this was not always the case.
Good work.
Then, astronomers using the Fermi Gamma-Ray Space Telescope identified two gigantic regions stretching above and below the
B1
galactic
și
crown,
anti-aer.
each one over 50,000 light-years across. Computer simulations revealed what caused them: a feeding event several million years ago. Whether it was a cluster of stars or a wandering clump of interstellar gas that met its end in the hungry maw of Sagittarius A star, our black hole destroyed it quickly, shredding it into an accretion disk around the event horizon. And then, the same physics went to work. The accretion disk energized a powerful magnetic field, which created jets and launched relativistic particles away from the galaxy, where they still sit
Nu
today.
știi că are uneori un aim de mă trezesc cu o rachetă între dinți de acolo.
Indeed, it seems that every galaxy has gone through at least one active phase, spending some of its life cycle as a quasar, with the central core of the galaxy, barely a few light years across, outshining not just its own galaxies, but 1,000 galaxies combined. But despite our growing comprehension of the incredibly energetic forces powering these vast dynamos, the quasars we see are still too bright. The supermassive black holes that serve as their gravitational
gonna
power
find out
sources are also
if it actually hits.
big. Too big. And they are not the only issues.
Like a wise woman once said, it's never too big.
Discover quasars appearing in the earlier universe. Too early. Quasars seem impossibly big and impossibly bright, existing impossibly early in the history of the cosmos. What does this mean?
Ok, pe mine zdreamța mică. I'm gonna figure out this plane, don't worry.
Everything about quasars is the very definition of extreme. The largest known supermassive black hole weighs over 66 billion solar masses. If you were to place that black hole in our own solar system, with its singularity at the center, by the time you reach the orbit of Pluto, you would be less than 1% of the way to its event horizon. We currently know of around 1 million active quasars, and suspect that there are at least 10 million more in the observable universe yet to be seen, each one pumping out more energy than 1,000 galaxies combined, each one a fierce engine of plasma and radiation. Quasars have been with the universe almost since its birth. The most distant known quasar, named J0313-1806, was firing when our universe was only 670 million years old. That's just 5% of its present age. Astrophysicists aren't quite sure how these black holes appeared so early and got so
Everything
big
looks the
in
same.
the relatively short age of the cosmos. The only way that we know for sure how to make black holes is through the deaths of massive stars. So by this logic, the first black holes couldn't exist until the first generation of stars died. If those early stars were like the stars of the modern universe, then they left behind black holes no more than a few times the mass of the Sun. From there, the black holes had to grow, and they have two options available: merging and accreting matter. Black holes, especially massive ones, don't merge all that often, at least theoretically. Initially, when two black holes encounter one another, interactions with their environments allow them to draw closer together. But eventually, all that's left between them is their own gravitational pull. As the black holes wind around each other, they emit gravitational waves, which pulls energy out of the system and allows the black holes to sneak closer together. Once the black holes are within a few light years of each other, sufficient gravitational wave emission alone would take longer than the age of the universe. Astronomers still don't have a solution to this obstruction, calling it the final parsec problem. Yet despite this, we do know they merge.
Just lost sector alpha to the enemy.
We have detected signature ripples in space-time from merger events.
Am intrat în stall, frate, din viteza aia, imposibil să intri în stall de acolo.
For supermassive black holes, we usually find only one residing in each galactic core, despite each galaxy having several multiple merger events.
Oh, helicopter.
The universe has clearly solved the final parsec problem. We don't yet know how. Now, However, even the most optimistic estimates for black hole production and merger rates can't explain the largest and earliest quasars. So that leaves the solution to give black holes their exceptional masses. But once again, we run into a problem. The same seesawing of radiation and gravitational collapse that keeps quasars illuminated for millions of years prevents large amounts of gas from reaching the black hole quickly. This process is known as the Eddington limit, and while not a hard and fast rule of the universe, it does present a challenge. If black holes are to reach supermassive status, they need to find a clever way around this, and somehow shove extra material through the event horizon without heating it up to the point that it escapes the vicinity of the black hole. Compounding this problem is the lack of observational evidence of so-called intermediate mass black holes. These black holes should sit in a mass range well above stellar mass black holes, which weigh only up to a few dozen times the mass of the Sun.
What's your after damage or
below
what the fuck?
supermassive black holes, which weigh millions or billions
Ce
of
unul și ce
solar
unul,
masses.
bun.
We should see these in-between class black holes everywhere, representing an intermediate stage of growth between the stellar mass and supermassive black holes. But we don't.
Da, meni dracu aici.
On the other hand, the results from gravitational wave detectors suggest that black holes are emerging far more often than we had initially assumed. In order to get the detection rates that we observe, many small black holes had to have merged in the history of the universe, meaning that they find each other, close their orbits and merge quite efficiently. In addition, those same results suggest that there are many more small black holes than we had initially assumed based on simple stellar deaths. The result is a confusing, tangled mess. It is clear our understanding of the growth and evolution of black holes is missing something. Traditional models of galaxy and star formation don't seem to be cutting it. So perhaps it's time to turn to more exotic models. One possibility is that dark matter itself can directly collapse to form black holes. Dark matter is the dominant form of matter in the universe, making up roughly 80% of the mass of every single galaxy. But in the simplest models of dark matter, it doesn't interact with itself, and so has difficulty clumping together at small scales. When it comes to something like a galaxy, most theorists assume that the dark matter is roughly evenly spread out. But in some more complicated models of this mysterious form of matter, it is capable of small, infrequent interactions with itself. This would cause it to clump together rapidly, especially in the high-density days of the early universe. And if enough dark matter clumps into a small enough volume quickly enough, then its own gravitational weight can take over, leading to catastrophic collapse and the formation of a giant black hole. A black hole potentially big enough
Mogą patrzeć
to
damage
begin
wulkanu,
powering
domne teraz
quasars
naskok.
before the first stars had even arisen. Another possibility is that our assumptions about star formation don't apply in the early universe. In today's cosmos, stars can only get so large. This is because the nebulae that collapse to form them can only grow to a certain size before they begin to efficiently lose their heat and collapse. But that efficient cooling depends on the presence of heavier elements to radiate away the energy of the nebula. The early universe, however, lacked such heavier elements, because massive stars have to live and die to enrich the interstellar medium. So perhaps stars hundreds of times more massive than the Sun could form. If those giant stars die, they would leave behind much larger black holes. Or perhaps the solution is something even more exotic. Maybe black holes have been with us since the earliest moments of the Big Bang. In this scenario,
What the
the
fuck?
exotic conditions and phase
Pomul ăla
transitions
trage
of
de
the
nu m-am
first few
văzut.
seconds in the history of the
E1.
universe spawned
E1.
countless small black holes, known as primordial black holes. Though many observations have ruled out the existence of black holes like these, there is still the possibility of their existence. There may not be a lot of them, but if enough survived into the age of galaxy formation, they could provide a shortcut to quasar building,
Acum mai safe.
bypassing the usual route of star and black hole formation. It's these questions and many more that provided motivation to build the James Webb Space Telescope, which is currently probing the first generations of stars,
Morto.
galaxies and quasars to appear in the universe.
Urât din partea ta, bă, cu misarul ăla așa perversă de bovna.
Regardless of these mysteries, one thing has
Bine
become
că n-am intrat în
clear.
stol aici, că rămâneam în pula mea în afara
Supermassive
combatului.
black holes are inextricably linked together. The formation of quasars plays a key role in that relationship. And in the early 2000s, astronomers made a startling realization. It's not just simply a matter of every known galaxy hosting a supermassive black hole at its center, but the properties of that black hole are closely linked to the properties of the host galaxy. For example, the greater the black hole mass, the higher the temperature in the galactic core, and the higher the stellar velocity within. And the larger the black hole is, the more massive the overall galaxy is. And so it appears that supermassive black holes don't evolve independently of their host galaxies, and turning on and off quasar activity plays a key role in that self-regulating connection. The galaxy accretes a lot of material, either by gravitationally attracting gas in its surroundings, or by cannibalizing another galaxy. That galaxy now has a lot of new material to boost star formation. But a lot of that material winds its way into the core, which turns into an accretion disk and launches a jet, turning the core of the galaxy into a quasar. All that radiation envelops the black hole's host galaxy, heating the entire contents of its interstellar medium. If the gas is too hot,
Sorry bro, I
stars
fly
don't
too
form
low.
efficiently. This means that what would have been a burst of sudden star formation turns into a steady trickle. If this is good for the
Can't lock
galaxy,
me,
too much
bitch.
star formation at once would use up all the available reservoirs of gas, which would ultimately end star formation too soon. But the quasar acts like a brake, preventing too many stars from forming in a short period of time. It seems almost every galaxy has gone through a quasar phase, and these galaxies continue to regularly pump out new stars at a predictable, efficient rate. This quasar back and forth explains the relationship between galaxies and their
Gata, anti-aero.
supermassive black holes.
Mai am un avion aici care mă fute la melodie.
Hole, and feedback from the quasar keeps star formation in check. And this also applies to our own galaxy.
Lapsuri on. That's third.
The Milky Way grew from countless mergers and cannibalizations of super galaxies. And each one of these interactions could have flooded the galaxy with so much new
Damn,
material
I didn't know about
that
this
star formation
flaps.
became uncontrolled, using up all the available
breakers.
gas in just a few hundred
They are in
million
War
years.
Thunder, though.
But Sagittarius A star kept us in check, preventing stars from forming too quickly. Indeed, it could be that without Sagittarius A star activating as a quasar deep in our distant past, then our own sun may never have formed, and we may never have been here.
Yeah, the sun is our
But
true
this happy
father.
equilibrium will not last long. In 5 billion years, our galaxy will begin to merge with our nearest neighbor, the Andromeda Galaxy. Our two supermassive black holes will find
F1.
each other.
Ba nu,
Also
între... Da.
material, tattered
Nu
remnants
de ce
of
unul.
stars and nebulae destroyed
Nu
by the
intra în
gravitational
stol.
forces of the merger will find its way into the new core. When it does, the slumbering giant in the center will reawaken, activating its mighty engines of gravity and magnetic fields, and pouring its tirelessly fierce radiation into the new galaxy, snuffing out any hopes of peace and quiet for ages
Oh, fuck.
to come.
Time to turn this battle around, troops. We must claim more sectors.
Bombardier to your
You've been
stations.
watching the entire history of the universe. Don't forget
Red
to like
alert.
and subscribe and leave us a comment to tell us what you think.
Altul.
Thanks for watching. See you next time.
The enemy controls Sector Alpha.
What is the biggest thing in the universe?
My penis.
In 1985,
Did it, did it.
geologists believed that they had found the answer. A team led by John Huckrow at the Harvard-Smithsonian Center for Astrophysics had just completed a survey of the galaxy in
Ooh.
the direction of the constellation
Full of sand.
Coma. But as they looked through the results,
Lasă mă duc
they
dracu.
noticed something odd. Stretched across hundreds of millions of light years, a shape began to slowly appear
Nu e un vehicul pe undeva pe aici, nu mă risc.
Sector Delta.
of a person. A stickman.
Aia e unul.
But the
Totul în gură,
creature,
anti-aer.
long, slender torso,
Dă-ți au
outstretched
anti-aer, frate, în
arms
locul
and
ăsta.
dancing legs, was no monster of ancient legend. It was one of our first glimpses of a supercluster. And it was not alone. Our observable universe turned out to be full of superclusters, roughly 10 million in total, each one containing tens of thousands, even hundreds of thousands of galaxies. Indeed, our own Milky Way is nestled inside of one, known as Laniakea, on one of its outer limbs. And these superclusters are massive. At their smallest, they're several hundred million light years long, composed of lacy
Suddenly he
and
targets me,
branches
fuck
and
off.
clumps of galaxies. The largest
Leave
stretch
Britney
across
alone.
the heavens for up to
I gotta
10
tell you something.
billion light years, and their enormous volume is matched only by their mass. A typical supercluster contains over 10 million billion suns worth of material. The nearest superclusters in
E ca Tyrian, numai un pic mai complicat.
appear through to map
Da, săracul Tyrian.
Coma, the Virgo, the Hydra Centaurus, the Pavlindus. More distant ones are usually given simple catalogue designations unless they break some record in size or distance. For example, the King
Iar auzi, e un fel de apaș.
supercluster, one of the most massive
Mă
yet
cherusesc.
mapped, was discovered in 2022 by a team of Japanese scientists who named it after the three-headed nemesis of Godzilla. Despite the monstrous size of these superclusters, their ability to encompass hundreds of thousands of galaxies at once, the way they bridge across light years with strings of dazzling points, they are small. For there is a far larger, far more menacing class of entity inhabiting our cosmos. The true largest objects in the universe are nothing. These are no titans of ancient myth or kaijus of modern cinema. They are the opposite, a shadow in the dark. For most of our universe is void,
You are overwhelmed.
nothingness.
We must take our losses
There
and
are
Mă fac
no
un gard
lights
de
to
fit,
trace
cum
their
dracu.
structure,
Nu
no
mergeți pe
gaseous
punct, bă.
filament to highlight their nature.
Nu mergeți pe
We
punct.
can only
Bă,
detect them through their absence.
oh my god, ce
Cosmic
fain e avionul
voids
ăsta,
are the
incredibil.
single largest objects in the universe. They define the superclusters, they define our existence.
Really nice plane.
Everything we know and love,
I'm
our
glad
own
they-
solar system,
they
our
pay
galaxy,
attention to
our supercluster,
2042.
all exists suspended on the edge
Okay.
of the abyss.
Gata, 99.